Hello, I'm Arjun Berera, and my research area is particle physics and early universe cosmology. In today's lecture, we will be talking about the theory of special relativity, which will lead to the well-known relation between mass and energy of Einstein. This will be, for example, relevant in the case of converting energy into mass, such as at the Large Hadron Collider. We start by continuing our discussion of light. For centuries, physicists had been debating and discussing the nature of light. In particular, was light a wave or was it a particle? It would not be until the beginning of the 20th century and the advent of quantum mechanics that it would be understood that light, like matter, had a dual nature of being both a particle and a wave, which is something that we will be discussing in future lectures. But at the start of the 19th century, some convincing experiments by Thomas Young led to the prevailing belief that light was a wave. This eventually, and later on in the century, culminated into the equations of Maxwell, which were discussed in the previous lecture, which described the propagation of light and other forms of electromagnetic radiation. But if light was a wave, physicists reasoned back then that there had to be some medium in which this light propagated. Certainly all other waves that physicists knew of propagated in some medium, such as sound propagates through air. Thus, light, for example, could come from the sun through an empty void of space. Very good vacuums could be built in the laboratory, and light could propagate through it. So it was hypothesized that there was some material, which was just called ether, which permeated all of space, and this was the medium through which light propagated. The ether formed an absolute reference frame in the universe. It was a backdrop upon which all of physics was believed to occur. Light was believed to propagate at a fixed velocity through the ether. A decisive experiment for testing the ether hypothesis was done by Michelson and Morley near the end of the 19th century. Since the Earth orbits around the Sun, it means that the Earth's motion relative to this ether must be changing during the year. Michelson and Morley exploited this fact and developed an experiment to test for the ether. The apparatus they built is called an interferometer. It consists of a light source with the light beam going to the center. The beam is then split into two beams which go perpendicular to each other and travel equal distance L. Each beam then hits a mirror and then bounces back to the center, where both beams combine together again and go to the detector. Suppose this interferometer is moving at velocity v through the ether in this direction. Then, for the light beam going parallel to the motion, suppose the journey to the mirror takes a time t parallel 1. Light is traveling at speed c through the ether times t parallel 1. This light must go the length L plus the additional amount the final mirror traveled in this time, which is v t parallel 1. Thus, solving this, we find t parallel 1 is equal to L divided by c minus v. To see this another way, if the interferometer is moving at velocity v in this direction with respect to the ether, it's the same as the ether moving at velocity v in the opposite direction with respect to the interferometer. Thus, as the light moves in this direction, it is moving in the opposite direction to the flow of the ether. So the velocity of the light is slowed to c minus v. It's similar to if you were swimming upstream in a river. As you move forward, the river flow, which here is like the ether flow, carries you back. Now, looking at the journey back from the mirror to the center, it is now in the direction of the ether flow, so the time to go back is t parallel 2 equals L divided by c plus v, giving a total time for the journey to and fro of t parallel equal to 2 times L times c divided by c squared minus v squared. For the journey across the ether, applying the Pythagorean theorem for a right triangle, shown in this diagram, we find the time to go up and back from the mirror is t perp equal to 2 times L divided by the square root of c squared minus v squared. So we can now determine the time difference, t parallel minus t perp, to be L over c times v over c squared. The beam going perpendicular to the ether flow will arrive sooner than that going parallel. Thus, the two light beams going these two different directions, when they combine again, will have slightly shifted waves, which can then be detected. When the experiment was done, it showed there was no such shift in the light waves. After the null result of the Michelson-Morley experiment, physicists were a bit confused and were scrambling to find an explanation. Many physicists still wanted to adhere to the ether idea, and various ideas were proposed, like, for example, perhaps the ether was being dragged along with the Earth, and therefore there was no relative motion. However, most of these ideas proved unsuccessful. There was one idea proposed by Fitzgerald and independently by Lorentz, which was that in the direction of motion, an object gets contracted, the length gets contracted. Lorentz even went as far as to produce an exact formula for the amount of this contraction, and that could precisely explain the Michelson-Morley experiment. However, this idea led to various questions about the nature of forces, and are all forces going to contract in that direction, or only the electromagnetic force? Basically, it led to various complicated questions. Then, in 1905, Einstein proposed his special theory of relativity. The second postulate of relativity is actually quite unintuitive. For example, if I have a beam of light, for example, I have a little flashlight here, and it's got a beam of light, and if I measure the velocity of light, and suppose I'm at rest with you, and I measure this velocity, so I measure some value, c, actually it's 300 million meters per second, and you measure the velocity of this light, you would measure exactly the same number. Now, suppose I'm moving relative to you, and while I'm moving, if I now measured the speed of this light, I would measure the same number because the light source is at rest with me. But because you're at rest, because I'm moving relative to you, even then, what special relativity says is that if you measured the speed of light, you would measure the same number that I did. This is quite different from what we normally expect. Suppose, for example, that I have a ball, and I do the same experiment. So I'm standing here, I'm at rest with you, and suppose I throw the ball. So when I throw the ball, I measure some velocity v. And when you measure the velocity of the ball, you would measure exactly the same number, v. Now suppose that when I throw the ball, I'm moving relative to you. Now, let's just suppose that I threw the ball at the same velocity. So when I measured the velocity of the ball, I measured some number. Now you, who are sitting at rest, and I'm moving relative to you, you would say that the velocity of that ball was my velocity plus the velocity that I measured of the ball. So you see, this is quite different from what Einstein is saying about light. What he's saying about light is that even if I'm moving, no matter if I'm moving, the velocity that I measure of light would be the same as the velocity you would have measured. The postulates of special relativity lead to several consequences which are unintuitive. For one thing, they completely altered our notion of time. We can see this from a simple example. Let us consider a clock composed of two mirrors separated by distance little d, and between them a light pulse bounces. The light pulse, going from the bottom mirror to the top mirror and then bouncing back to the bottom mirror, can be regarded as one unit of time, or a tick of this light clock. Let us place two identical light clocks, one in what we will call the laboratory frame, which is at rest, and one in a rocket frame, which is moving at velocity v with respect to the lab. With respect to the lab frame, the clock on the rocket travels a longer path, since it must make this diagonal path. Since the speed of light is the same in both frames according to special relativity, the lab frame will conclude that a light pulse in the rocket clock completes a cycle going from the bottom mirror to the top mirror and then back, or a tick of the clock, in a time we will call t sub cr, that is longer than the time it takes the lab clock to complete a cycle, which takes time t sub cl. So the lab frame concludes the moving clock in the rocket is moving slower, or in other words, the rocket clock takes longer for one tick. If the clock in the lab frame measures some interval of time, delta t, then the time interval the lab frame will see the rocket clock to have, delta t prime, will be reduced by the ratio of little d over big D. We can compute big D using the Pythagorean expression. Big D is the hypotenuse of this right triangle. One of the sides is little d, the length of the light clock. The other side is 1/2 v times t sub cr. In other words, half the distance the light clock travels in time t sub cr. Thus, big D squared is equal to little d squared plus v over c squared times big D squared. Rearranging, we can solve to find that big D is equal to little d divided by the square root of 1 minus v over c squared. This means delta t prime is less than delta t by this factor, square root of 1 minus v over c squared. This is how much slower the rocket clock is going with respect to an observer at rest with the lab clock. The length of objects also are affected in special relativity. Looking again at the lab and rocket systems, suppose now we have a rod which measures length L sub 0 prime in the rocket frame where it sits at rest. Here the zero subscript means proper length, which is a terminology for length of an object measured in the frame where it is at rest. Let us measure the length of the rod in the lab frame by noting the times t1 and t2 when the front and back of the rod respectively go past point P. Then the length of the rod measured in the lab frame will be L equals V times t2 minus t1. We will call delta t the time interval t2 minus t1. The times t1 and t2 in the lab have corresponding times t1 prime and t2 prime measured in the rocket, with L sub 0 prime equal to V times t2 prime minus t1 prime. Similarly, we will call the time interval delta t prime as t2 prime minus t1 prime. With respect to the rod, the lab clock is now moving, so its time is slowed as delta t equals delta t prime times the square root of 1 minus v over c squared. So L is equal to v times delta t, which is equal to v times delta t prime square root of 1 minus v over c squared, which is equal to L naught prime times the square root of 1 minus v over c squared. Thus, the length of the moving rod has contracted when measured in the lab frame. Note that this is the same expression for length contraction that Lorentz had initially derived, but the interpretation of it in special relativity is very different from what Lorentz had proposed. In fact, Lorentz had initially derived the expression for time slowing down that I had just showed, but again, his interpretation was very different from that in special relativity. Notice how the results for time slowing down and length contraction all have these factors of square root of 1 minus v over c squared. In special relativity, no material object can ever go faster than the speed of light. Even in the example I showed earlier of throwing the tennis ball, I said the velocity is additive when I am moving and then throw the ball. In fact, it's not exactly additive. There are small corrections. But the velocities of the ball and myself were much smaller than the speed of light, so these corrections are unnoticeable. But once velocities reach near the speed of light, these corrections become important and act in such a way that no velocity ever gets bigger than that of light. In special relativity, if two events are measured with time separation delta t between them and length separation delta x between them, then it turns out that the quantity c squared delta t squared minus delta x squared is the same number with respect to coordinates in all different frames moving at constant velocity with respect to each other. And recall c here is the speed of light. Let's look at an example. In the previous case, where the length of the rod was measured, in the lab frame, a time delta t lapsed between measuring the front and back of the rod. Both measurements were done at the same point in space, so delta x was equal to 0. Now, in the rocket frame, the time lapse was delta t prime between the measuring the front and back of the rod, and there was a spatial separation delta x prime equals L sub 0 prime. We also have that L sub 0 prime is equal to V times delta t prime. Let's now check the value of this invariant interval expression in both frames and ask ourselves whether the two are equal as expected by special relativity. We ask, does c squared delta t squared equals c squared delta t prime squared minus delta x prime squared, which is equal to c squared delta t prime squared minus v squared delta t prime squared. We had that delta t is equal to delta t prime times the square root of 1 minus v over c squared, by the relation for time slowing down. Inserting this above, we find indeed that this expression for the invariant interval is the same in the two frames. Finally, we now look at the relation between energy and mass. For this, let us look at the motion of a particle of mass m in two different frames. We will call the prime frame the one at rest with the particle, and the lab frame the one where the particle is moving at velocity v. In the particle frame, at all times t prime, the particle is at position x prime equals 0, since, as we said, the particle sits at rest in this frame, so its spatial coordinate never changes. If we now take the derivative dt prime, it equals 1, and dx prime dt prime is equal to 0. Recall here that in the mathematics of calculus, the derivative, for example, dx prime dt prime, is simply the ratio of x prime at t prime plus delta t prime minus x prime at t prime, all divided by delta t prime, in the limit that the time interval delta t prime gets smaller and smaller. So the expression m squared c squared dt prime squared minus m squared dx prime dt prime squared is simply the same old invariant interval we just discussed, meaning c squared delta t prime squared minus delta x prime squared, except with both expressions basically divided by the same factor of delta t prime squared up. Also note I multiplied the interval with an overall factor of the particle mass squared, m squared. So what we get for the invariant interval expression is that it is equal to m squared c squared. Now let's look in the lab frame where the particle is moving. So at time t in the lab, the particle is at position x. We have that mc squared dt prime, which we are simply calling p sub t. Note here we take the derivative with respect to the same quantity t prime, and we have simply called the expression pt to give it some name. We also have m dx dt prime, which is equal to mu equals p, which is just the momentum of the particle. So we have, for this interval, p sub t squared divided by c squared minus p squared. And since this expression must equal the invariant interval in the particle frame, it means that it is equal to m squared c squared. This, therefore, leads to the relation that p sub t is equal to the square root of m squared c to the fourth plus p squared c squared. When the first term is much larger than the second in this expression in the square root, we find that p sub t is approximately equal to m c squared plus p squared over 2m. This second expression on the right-hand side is simply the kinetic energy of a particle of mass m. So we identify p sub t as the energy of the particle. In other words, p sub t is equal to E. So we have the general relation that E squared is equal to m squared c fourth plus p squared c squared. As such, when the particle is at rest, when p is equal to 0, we have the famous relation that E is equal to mc squared. But this expression is more general and tells us the energy of a particle also when it is moving with non-zero momentum p. It tells us energy is equal to the mass of the particle plus its energy of motion through the momentum p squared term. So this relation tells us the equivalence of energy and mass. For example, in nuclear reactions, such as an atomic explosion or at a nuclear reactor, it is mass that is then converted to energy. But this relation also tells us of effects that work the other way. For example, in the Large Hadron Collider, which is looking for the Higgs boson and other particle physics, there are two protons with a lot of kinetic energy between them that hit together, and a lot of that kinetic energy, or energy of motion of these protons, is then converted to particles, thus to mass. This concludes our discussion today of special relativity, and we now understand the origin of the relation between mass and energy. Thank you.